Good morning. So we're going to go through a little bit more detail what we talked about yesterday. And as you heard, fluoro, that was a great fluoro talk. And fluoro has one of the big advantages we have in doing supine direct anterior. This is another potential technology. Here are my disclosures. So why use navigation and robotics? Why? Well, we know that many of the reasons for revision can be linked to malpositioned acetabular components, and you can see the list here of those. Multiple studies have shown that we can get more accurate acetabular component positioning with navigation in hip replacement. This is a study out of Japan looking at hip dysplasia patients. Multiple studies have also shown lower dislocation rates if we use navigation and hip replacements. And in fact, this study with the Australian registry showed lower revisions for all causes with navigated hips. So why use navigation and robots? The one thing we're going to talk about today, there's multiple things, but cup positioning. We know that all of us have a different pelvic tilt when we go from sit to stand. And because some people shift a lot going sit to stand, others don't shift at all, we can adjust our component positions to account for this. Our ability to do this manually is limited. So I'm going to show you, here's looking at someone, here they are standing, and you can see how their pelvis, and then we sit, and we go from, now we're standing, now we're sitting, and this is someone with a very stiff spine, and you can see how they're really not moving very much as they go from, that was their sit, and now we're going to change, and we're going to go to the typical mid-range of how much someone shifts from sit to stand, and watch how much, here's sitting, now watch when they stand, look at how much the pelvis changes, going from stand to sit. This is average, okay? Here's that same patient standing, and when they sit, the pelvis rolls back and they get some more anteversion. But every human being does this differently, and we can't always know if someone's had spine surgery or not. You can have had no spine surgery and have a very stiff spine. So here, by adjusting our components that we talked about yesterday, we're going to put our components into a virtual range of motion. So you can see that we're externally rotating our construct as we plan it, and the red is where we have impingement, okay? So we can see we're adjusting our head size, and the head size will minimize our component-to-component position. And now we go to sitting, and we're going to internally rotate. You can see how we're internally rotating, and you can see there we got some red at the anterior-inferior spine, so we're getting bone-to-bone impingement. Okay, and if we go back to standing, sitting, we can see where we're getting impingement before we do the surgery. Now we're going to look at just pure hip flexion. So we're taking out all the internal rotation, we're just going to flexion, and you can see we can get up here to 140 degrees and still don't really have impingement. So we can do this ahead of time and find out where we're going to have a problem, and we can adjust our components accordingly. So each patient gets a patient-specific CT scan, and we're going to plan the surgery in 3 dimensions. And I'm going to just zip through a quick case as an example. Here's somebody you can see they have posterior osteoarthritis. Traditionally, we do now, this is the old acetate templating. Digital is clearly better, I think, but you can see that we're doing 2-dimensional templating here. And with the patient-specific CT scan, it does allow us to do 3-dimensional planning. So we're surgeons, we look at x-rays, so I always start with the x-ray view. Then we're going to go to this cartoon view, and we're going to adjust it. This is the reaming view. In the large picture, the green is the bone we're going to remove. And most of the work is done with a picture-in-picture view. So you can here's the transverse picture. We can look anteriorly and see that we don't have acetabular component overhanging the anterior rim of the acetabulum. We can judge our reaming depth. We can look at this in all 3 planes, the transverse, sagittal, and coronal, and we have all 6 degrees of freedom of how we position this component. We decide where we're going to put it, okay? Once we've done that, we can look at the femoral plan, and I'm used to looking at x-rays, so I always start with the x-ray view, and then we can go to this cartoon view, I call it, and we can look at it in the sagittal as well as transverse planes throughout the entirety of the stem. We can measure where our neck cut should be, above the lesser trochanter, or there's other landmarks we can use to get our net cut measured and made very precisely. And so this is the X-ray view of our plan. This is what we think it's ultimately going to look like. So then intraoperatively, as we talked about yesterday, we register the acetabulum so that the computer has correlated the actual patient's anatomy with a CT scan. So the computer knows where the acetabulum and pelvis is in space. We can then bring in the robotic arm, and the robotic arm will carry out that plan with a very high degree of accuracy and implant it. And Seth Jerebick, as I mentioned yesterday, has done a post-op CT study where he showed that the robot was within 1.5 degrees of our planned position. And here is this particular case, his post-op film. You could see we did lengthen him intentionally, knowing we're going to come back and do the other side. So here's a study from China where they looked at the ability of the robotic technology to implant things where we had preoperative planned them, and it showed very high correlation with that. So to summarize, navigation and robotic assisted cut positioning allows patient-specific 3D planning, and then we can carry out that plan accurately. Thank you.